Hello everyone. Today we'll talk about the solution to the problem minimum number of changes to make binary string beautiful. When we are solving this problem after reading the statement, we might want to imagine what a beautiful string looks like. Well, of course, a beautiful string will be a sequence of blocks. Every block consists of characters of the same type, so they have alternating ones and zeros. And for a beautiful string, all of those blocks have to have even length. It's always possible, given that the original string has even length, to make the string beautiful. For instance, we can just make it one big block of ones or one big block of zeros, but it's unlikely to be the best solution. So we might wonder what a single move will do to this sequence of blocks. Because a single move will not modify blocks all over the place, it will only modify some blocks right next to where we're making that move. So, for instance, if we try to make a move within a block, that doesn't seem to be very helpful, because if we have a block that's even, then it doesn't really make sense to change that block, or at least it doesn't seem to make sense, because then we create two new odd blocks. So for instance, if we split it in half and change the character to the right, then we have an even block, a one character odd block, and the remaining odd block. So that seems pretty pointless. And if the block is odd, then by flipping a character in the middle, then we do get two even elements, two even or two odd parts. But we also have this single element odd part in the middle, and it seems even more difficult to do something about it. So it's probably likely that we'll be trying to make flips at the end of blocks. So, okay, that would be one idea that we can have. It's also probably not a bad idea to make flips in such a way that we make our current block larger and not smaller, because then we have more of a string being already correct. Because of course, for a string to be beautiful, every prefix of that string that ends at the end of any block will have to be beautiful. And since we don't want to make those flips in the middle of blocks, we can just consider if we have, let's say, an even block, an odd block, even, odd, odd. Because of course we have to have an even number of odd blocks, since the whole string has an even number of characters. And now what we see is that what we can do, we don't want to do anything with even blocks, and when we have an odd block, we can change it to an even block by changing the next character, and in that case our odd block becomes an even block, and we flip the parity of the next block. So it's great for us if we have two odd blocks next to each other, and we're not too happy if we have an odd block and then an even block, because then we transform this one into an even block, this one into an odd block, because we change the first character of this even block to be the same as the characters in this odd block. And of course, to end the solution for this example, we flip this one to an even, this one becomes even, and we have performed three moves. And finally, we can convince ourselves that this is indeed the best solution, because we have to do something, for instance, about this first odd block. And as we have established that there is no point in making a flip in the middle, it will only make things more difficult. And of course it doesn't make sense to make this block odd, because then we have even less of a string that's already covered. Then we have to flip it somehow, and in that case we also flip the next block. So we can simulate that process. We'll again be just going through all the characters in the string and remembering the size of a block. So we remember the previous character, whether the number of occurrences of that character were an odd number of occurrences or an even number of occurrences, and of course the number of flips that we had to make. And now whenever we see an end of any block, then we just look if the previous block was odd, and in that case we have to flip the next character. So we have to perform a flip to fix that block. We'll be flipping the next character, so we don't have to do anything, we don't have to change this value of odd. And of course, whenever we see a next character, we can flip odd to be different from what it is at the beginning. So this may be unclear here that we don't really reset this odd value, but that's because if the block was even, then we see a new character and it occurs not even, so an odd number of times. That's great. If the previous block was odd, then we see a new character. It occurs an odd number of times. But our odd was already set, so not odd is even. So now we'll remember that it occurs an even number of times, but that is correct because we have to flip that character. We've decided to flip that character. And we can also notice that, because typically when you write the loop like this, you have to have an additional check at the end. This check is not necessary here, so you might want to wonder about what would happen, so why it's not necessary in this problem. And some other thing that you can wonder about when looking at this solution is that you may come up with a simpler solution. In fact, there is a one-liner solution, or there is a specific way of a specific condition to check that's a bit different from this approach, but it checks the same thing, and it allows the solution to be contained in a single line. So it's a challenge for you to either come up with it or to find that solution in solutions published by people, because people publish solutions and some of those solutions will be this one-liner solution. As a hint, that one-liner solution will determine the number of times where we have, so the number of odd blocks, by just looking at neighboring characters. By just comparing neighboring characters, but we don't even have to compare all the neighboring characters, but we can pair them up, first two, the next two, the next two, and compare all those pairs whether or not we have a flip. Because if we have a flip within a pair, or it's not within a pair but between two pairs, the number of times the flips within a pair occur will allow us to calculate the number of flips necessary to solve the problem. So this is a challenge for you. And also another thing you might want to wonder about is what if this string was not a binary string, but it could have any values and not just zeros or ones, how the solution changes in that case.